Hi, everybody, and welcome to the Renewable Energy Lab for Engineering Tomorrow. My name is Eric Einset. I'll give you a quick background on me in just a minute here, but the renewable energy is a big deal these days as we're trying to decarbonize our economies and try to reduce our impact on climate. Renewable energy is becoming a big deal. So this lab is about understanding a little bit about how wind and solar energy works and how these natural resources, the wind and the kinetic energy in wind, and the photons that the sun shines and hits us with, can be converted into energy that we can use. So just as like all of our breakout labs in Engineering Tomorrow are designed by engineers, so I actually helped design this one. This has kind of been an evolution over many years, the wind and solar labs. And as usual, we have some college engineering students that are also involved. And this last summer, Anna Martelli and Jackie Lassiter, who are college engineering students, helped put this lab together in its current form. So just to give you a little background about me, I'm actually a chemical engineer, and you may wonder, how does chemical engineering fit into renewable energy? Even though I was trained as a chemical engineer, in my career, I've kind of continued to learn and as an engineer and understanding basic engineering processes and fundamentals of math and science, you can apply these skills really in a lot of different fields. And in fact, my latest work has been in renewable energy. And here are some pictures that show you some of the areas that I've been working in. We're actually quite active in offshore wind in my company. You can see the picture up on the top left, and also somewhere in the middle there, pictures of me on the top of an offshore wind turbine. And on the right, you can see a picture of the view across the ocean. You'll see the turbines, and then there's what looks like a little house kind of at the middle of the thing. That's actually a substation where the power gets connected from the turbines and then gets transferred to land. The pictures, there's a couple other pictures in the middle there. You can see me next to some solar panels. This is actually in Japan. And down below there, there's a picture of the solar farm that's being constructed. You can see the foundations and the structures that they put in place to mount the panels. So anyway, even as an engineer or a chemical engineer, engineering skills are something that can allow you to apply your skills to a lot of different areas. And as I said, renewable energy is a very important topic these days. And I'm really enjoying working on that. I mentioned what kind of engineers work with renewable energy. The thing is, these wind farms and solar farms are really massive projects. They're very expensive. There are a lot of elements to it. You have to worry about foundations. You have to worry about water runoff. You have to worry about the structures. You have to worry about this equipment is built and designed by mechanical engineers that are building the motors. Electrical engineers are looking at the generators and the electrical power that's being converted and then also transported around to land or to houses. So there's all kinds of different engineering that go into it. In fact, the whole area of decarbonization, the whole area of energy and power it shows up in a number of different of the engineering grand challenges you can see on the right. For example, try to figure out how to use fusion more effectively to provide energy, sequestering carbon, which means capturing carbon from fossil fuel-based energy sources and basically storing it and putting it away so it doesn't go into the atmosphere is a big area. And then also solar energy. Obviously there's a lot of energy in the sun, and we'll talk about that. So all kinds of engineers work on renewable energy. So if you're more focused and have more an enjoyment around electricity and electronics, there's an area for you. If you're more interested in structures and foundations, there's an area for you. If you're more interested in aerodynamics and materials, because there's advanced materials that go into building these things. So there's all kinds of areas where engineers can work in renewables. So this lab, you're going to learn about how to think about the power from the sun and the wind. We'll do a little bit of basic math to give you a feel for how this all works. And you're going to be actually building and designing and building a hybrid wind and solar structure to capture the wind energy and energy from the sun. And we want you to build a little house that you can actually light up with these LEDs from this renewable source. So just to go through some of the conceptual basics. The starting point really is understanding a little bit about how power and energy works and what's the difference between them. Now, if you take physics, if you've had physics or you will be taking physics, you'll definitely learn about energy and power. Energy, you probably know, comes in different forms. There's kinetic energy, potential energy, electrical energy, and energy is really the capacity to do work. Which means, your ability to actually consume or do something, such as lifting something or heating something or spinning a motor. This all takes energy. Now, that is different from power. Power is how fast you can do work. One of the analogies I like to think about is if you're a runner, if you want a short race, you want to run with a lot of speed. You need a lot of power to run fast. But if you're running a marathon, you're not going to run your fastest the whole time. You're going to need a lot of energy because over time, it takes longer. You're going to consume your energy, and you need a lot of energy for that. So that's the difference between energy and power. In this lab, when we're talking about electricity and renewable energy, we're going to talk about power and the energy in the units of watts, and the units of watt hours. Now, in physics, you'll probably learn about different units for energy, things like joules and calories and BTUs and maybe electron volts. But in electricity, it's really watt hours. That's the units we'll use. And power is, again, typically in watts, but you may also know the unit of horsepower. But all these units can be converted between each other. We'll talk about power and energy in large numbers. So quite often we'll be talking in terms of thousands of watts or thousands of kilowatts or millions of watts or kilowatts megawatts, sorry. So usually you'll see a kilowatt, a megawatt, maybe a gigawatt. Those are the units, and that's kind of what we talk about. Now, just to give you a feel for how big a watt is, if you think about a light bulb, an old light bulb that was a hot filament, a typical light bulb would be something that drew the 60 watts. You can see that in the bottom left. Now, as light bulbs are being converted to LEDs, they don't require as much power in order to light up, and they can actually consume a lot less energy over time. So you can see that other light bulb that's called Firefly, it only takes 7 watts, which is a lot less energy consumed. Now, if you think about other utilities or other appliances in your house, the refrigerator, it takes a lot of power, but it's not always running. When it is running, when it is cooling, it may take 500 watts of power. But over time, it kind of turns on and turns off. It only turns on when the inside is getting warm. So over time, we'll more likely talk about that as total energy being used. So in this case, we say about in a year, your refrigerator may use about 4,000 watt hours or 4 kilowatts. At the bottom right of the slide, you'll see that we have the sun and the wind. So in the summertime, when you're outside, you can feel the heat of the sun. That's energy that's being converted. And to give you a size or a sense of the scale of the energy that's hitting the earth, the sun delivers about 1,000 watts per square meter. And as you can imagine, the more area you have, the more energy can be absorbed from the sun. So that's about a kilowatt per square meter. And we'll use that number a little bit later. Now, when it comes to the wind, when you think about the energy that's in wind, if you're standing outside and it's very windy, you'll feel that the wind is trying to push you over. That's the power that's in the wind. And if we take kind of just an average or pretty brisk windy day of 20 mile per hour wind, that is about 1,750 watts per square meter of area. And just like if you think about a sail, the bigger your sail, the more power you're going to get, the more you're going to be able to capture that wind. It's the same idea. It's an area calculation. So the 20 mile an hour wind is almost 2,000 watts per square meter. And the whole idea of renewable energy is to capture this energy that's coming naturally from the sun, that's naturally from the wind and the weather, and to convert it into electricity. And that's what this lab is all about. So let's start with understanding what are the fundamentals of how wind power works. This is just a description or a picture of a wind turbine, a typical wind turbine. It has a number of parts that are useful here. We'll start with the top. You'll see that there are 3 blades, and those blades are the blades, just like in an airplane, that capture the wind, and they rotate and they spin a rotor. And that rotor, you'll see in the next slide, is what is turning and is actually a big part of the conversion to electricity. Now, the equipment that rotor works with and that spins is inside a little box there. It's called the nacelle. And the nacelle is where a lot of the mechanical and electrical components are. And it's in the nacelle that electricity is generated. That electricity then goes down the tower. You can see the tower there. The tower needs to be tall because there's usually more wind up high. And you can see it's very big. Just to give you an idea of the scale of these turbines, you can see the little person there at the bottom. You can barely see them. They're so small. It's because these turbines they become so large. These wind turbines are so large so that they can capture more energy. And you'll see that that's a wind farm there. It's probably in a place where there's a lot of wind, where they can actually capture a lot of energy. Each of these turbines can generate enough power to power over 1,000 homes. And some of the larger turbines, these are kind of average size onshore turbines. Larger turbines, the ones that are offshore, can power, thousands, many more thousands than that. So how does a wind turbine convert the wind energy, the wind power, into electrical energy? This diagram shows how that works. First of all, you have the kinetic energy of the wind, which turns the blades and makes them spin. That drives the main shaft, which you can see is going into the nacelle. And that is how that wind kinetic energy is converted into kind of a shaft rotating energy. That energy then goes into a gearbox, or that main shaft goes into a gearbox. And a gearbox basically takes gears and converts a lower wind rotational speed or shaft rotational speed into a high speed. And that high rotational speed then is what drives a generator, which is number 4. And that generator is essentially the piece of equipment that converts the rotational kinetic energy into electrical energy. And then that electricity is then sent down the tower through electrical wires, and then is connected to the grid. Now, this is kind of a generic description. There are a lot of turbines that are different. There are some turbines that don't have a gearbox. There are some turbines that do a different electronics up tower versus do some of their electronics down tower. But this is the basic concept of how a wind turbine works. So if we want to get a kind of an engineering feel for how much energy we're talking about, the formula on the right here shows you roughly the power that's in the wind. And you can see that it goes as 1/2 the density of air. So if the density of air is high, you'll get more power out of your turbine, everything else being equal. So the density of wind is higher when it's colder, just as an example. It's also related to the speed of the wind cubed. And this is why the wind speed is the biggest driver of the power that you can generate. And basically, you want to find places where the wind is strong. Now, CP is the power coefficient, so it's kind of a conversion efficiency. So it's a good engineering number, and it's a good measure of how good your turbine is. And then the area is essentially the area that is swept by your wind turbine blades. And you can see below there a circle where you have the radius or the wind turbine blade length, and the area swept is just pi r squared. So if you want to try a calculation, I have at the top some basic numbers here: the density of air, power coefficient, and a blade length of 0.5 meter, wind speed of 10 meters per second. And you can see, first of all, you have to figure out how much area is being swept by the turbine. And then you can go in and you can calculate how many watts of energy you could produce. So if you had a turbine that had a 0.5 meter long turbine blades, you can get about 140, somewhere between 100 and 200 watts out of that turbine. Based on what you've just heard, what do you think is important about where we should place turbines? This is 3 pictures of some turbines. One on the left is an offshore wind farm in the North Sea. The one on the right is an onshore wind farm on the plains in Southern California, in an area called Tehachapi. And in the middle is a nice picture that basically shows a bunch of wind turbines on a mountain ridge. So, what factors do you think should go into where a wind farm should be built? So, if your first answer was that you want to find a place that has a lot of wind, that's correct. The first thing you need is wind. You want to have places where there is a lot of wind blowing, and offshore and out in sea, there's a lot of wind. That's why it's one good place. At this place called Tehachapi, where the Alta wind farm is, it's a very interesting geography where they actually get a lot of wind coming off the ocean. Because there's a desert on the other side of the mountains. And as the hot air in the desert rises, it pulls in cold air from the ocean. So it's a very good wind area. And then the picture in the middle, you can probably imagine up on the top of mountains, if you've done any hiking, there's a lot of wind up in the mountains. There can be. So wind is the biggest factor. But there's another interesting factor, a couple of factors you may not have thought about, is it's quite important that you'd like to have wind turbines placed not far from large population centers. So you want to have a place where the power that's being produced is being used. So you don't have to send it long distances. So that's another factor that's important. And then another factor that you may not have thought about is the access of the area for this large equipment. One of the reasons offshore wind turbines are so much larger than onshore is because it's easier to transport them from a port out to sea. And quite often these wind farms are in the wind is highest in remote locations, but it's important that turbines and turbine blades that are almost 100 meters long can be delivered and constructed. So this is a video just to show what it looks like, or how you actually would install a wind turbine. This is an onshore wind turbine. It's a couple of years old, so it's not one of the largest wind turbines, but it gives you a feel for all the equipment, the cranes, and all the process for installing and building a wind turbine. Now, you just saw how a wind turbine is assembled on land, but offshore wind is a bit of a different challenge here. And these pictures show you what goes into installing a wind turbine out at sea. The picture on the left, there's really two steps. First, you have to create a foundation. And the picture on the left is an example of the installation of a monopile, basically a single pipe that goes down as a foundation. That's being hammered into the seabed. And the seabeds, typically these types of installations are in water that's, anywhere from 20 to 50 meters deep. So it's pretty deep. What you can see on that picture, two things I want to point out. One is it looks like the vessel is floating in air. The reason for that is because that is actually called a jack-up vessel. That ship went out to that location, and then you can see the four legs. Those legs were then put onto the ocean floor, and that vessel was lifted up and is basically being held up on those four legs. So it's sitting still, and the crew can then work on installing that monopile. The other thing I want to point out is you'll see a lot of white around the vessel. That's actually a bubble curtain. What they do is they create a bubble curtain using air, and that bubble curtain reduces the noise as they're hammering this down. So that's an attempt to reduce the impact on the wildlife when they're installing a foundation. The picture on the right is now showing you how the turbine is then installed. And again, you can see this is another jack-up vessel. The vessel's floating, is up in the air, sitting on these four legs. And when it's stable like that, they're then able to install the tower and the wind turbine blades, just like you saw in the previous video. Now let's talk about how solar energy works. Solar energy is actually a huge opportunity. The graph on the left shows you how much coal, uranium, and oil and natural gas there are in the world. So this is in units of total energy. You can see it's not megawatt hours, kilowatt hours, it's terawatt hours. And it's actually terawatt years, which give you an idea of how much there is. These would all be consumable. On the left side of the graph, it shows the power that's being delivered, or that the power that the wind and solar and other sources can provide every year. So you can see the scale of the solar opportunity. It's an absolute huge opportunity if we can find cost-effective ways to capture that. And you can also see how big the world consumption is. So there really is an opportunity. But of course, just like everything, solar and wind has pluses and minuses, and we'll talk about what those are. So there's basically two ways that solar energy can be converted, or is typically converted to electrical energy. Let me start with the one on the right. In a solar thermal plant, you basically just have a bunch of mirrors. And what you're doing is you're taking the mirrors, pointing them at the sun, and then the sun's energy is reflecting, and you're trying to heat up what is essentially a liquid, or a hot oil, which you can't really see, but it's in those tubes that are at the middle of these curved mirrors. And then that fluid gets so hot that they can actually pump it and use it to make steam. And then that steam is used to run a turbine and make electricity. So that's one way of using the sun's energy. It's called solar thermal. The other way, which is what you'll be working on, is on the left, is a direct conversion of solar energy using photovoltaic, or PV cells. And that's the more typical technology that's used these days. You'll notice that those cells are all flat panels compared to the curved mirrors that are used in solar thermal. So this is a video that shows you a little bit about how solar thermal, or solar power, works.
While it may not be the answer to all of our energy problems yet, there's one energy source we have plenty of: sunlight. In fact, the amount of solar energy that strikes the surface of the Earth in 1 hour is more than enough to supply every person on the planet with electricity for an entire year. We currently have a number of methods to harness the extraordinary power of the sun. Most involve converting sunlight into electrical energy. So, how's it done? The most common way to perform this energy swap is by using a photovoltaic cell. These make up the blue solar panels you typically see on people's rooftops. Most photovoltaic or PV cells are made of the element silicon. When a photon or packet of energy from sunlight hits one of the silicon atoms in the cell, it knocks off one of the atom's outer electrons. These free electrons then make their way toward a metal conducting strip on the solar cell's surface. The strip transports this steady stream of electrons, the electrical current, out of the cell so that it can flow into the power grid for people to use. There are other types of solar power as well. Concentrated solar power, or CSP systems, use giant mirrors to direct sunlight onto a small target. The concentrated light is used to heat a fluid, which in turn is used to boil water and create steam that turns an electrical generator. The great thing about both of these solar energy systems is that they are totally renewable and don't emit any greenhouse gases. So why don't we produce all of our electricity this way? To begin with, solar technologies aren't particularly efficient. Most convert less than 25% of the sunlight that strikes them into usable electrical energy. To top it off, we don't have good ways of storing solar energy, so for the most part, we still can't use it at night or on cloudy days. In other words, even if we plastered every rooftop in America with solar panels, they still wouldn't completely replace fossil fuels. Finally, solar power costs more. PV cells have become cheaper to produce in recent years, but solar technologies are still relatively costly compared to coal, oil, and even some other renewables. If we can work out these issues, efficiency, storage, and cost, solar energy really could begin to replace a significant portion of the fossil fuels we consume. We're not there yet, but the technology is getting better and cheaper all the time.
So let's talk just briefly about how photovoltaic cells work. And I have to say, these cells are really an engineering materials marvel. They've been developed over the years. They really started, they were used initially in the Apollo program back in the 1960s. And the way these things work, and they've now become kind of full scale productionized, but the way they work is they're a combination of very specific semiconductor materials. What happens is that they get processed in a very special way to form N-type and P-type silicon. They're put together, and they obviously there's a lot of engineering that goes into this. But when the solar radiation or the solar photons hit the material, it creates a voltage difference between the two sides of the material. And this voltage difference then can be put into a circuit, and you can create power. You can extract the power. And what you're essentially doing is directly converting the energy in the photons from the sun to electricity. So it's another engineering invention, if you will, and development over time. And in fact, when I was in graduate school, I spent my research doing work on analyzing the chemical reactors that grew these materials. So there you have it. That's how chemical engineering can be involved in this from a more traditional point of view. So just to do a quick calculation around how solar or photovoltaic cells work, a PV cell is actually not 100% efficient. If we say that it's approximately 20% efficient, then what you really want to do is figure out, for the amount of power that I want, how much area of solar cells do I need? So if you look at the math that's on the right of the slide here, if we say that we want 3,000 watts of power at noontime, and if you remember before, I said the sun delivers about 1,000 watts per square meter at noon. You can do the math and show that what you essentially need is about 15 square meters of solar cells. So solar cells typically are smaller. You'll see solar panels are quite a bit bigger, but you can go through the math yourself and see how you can convert the amount of energy or the amount of area needed of solar cells in order to create enough energy. And that's essentially kind of how the engineering works in terms of making solar energy more practical and effective. So how does this solar energy, which is actually direct current energy, can get converted so that you can use it on the power grid? Again, there's a series of steps. On the left, you can see that you've got a solar panel, which has a number of small solar cells. That creates a direct current when the sun is shining on it. And then there's that current basically through a charge controller can charge up a battery. And you can see the battery system there. And then in order to make that direct current or DC power into alternating current, which is what our electrical grid runs at, you need to use something called an inverter. Now, that is, again, an engineering system designed in order to utilize the solar energy. Now, the solar panels are actually made up of a number of small solar cells. And the way they're hooked together is, if you remember from the last slide, each of those silicon solar cells only generates about half a volt of potential. So in order to make that to create more power, because that's not a lot of power coming out of a half a volt solar cell, you have to hook these together in a series circuit, which you may have seen before in some of our other labs. And on the right, you can see how these series circuits, which are just like batteries, you can think about them as batteries, they just add up their voltages. So if you had an array of 9x8 array of these cells, that's 72 cells, each of them half a volt, you can figure out that that'll be about 36 volts total. So that's how you can think about the math, the converting individual PV cells into a larger application. So question just like I asked about wind, where is the best place to put a solar power plant? That's going to be where there's a lot of sun. And if you look at the map in the middle on the bottom, you'll see that, yes, that is where it's the darkest, where there's the reddest color shows where there's the most opportunity for solar energy. And it's going to depend on where you are on Earth, so where you get the strongest sunlight, but it's also going to depend on what your weather is. So if you have a lot of clouds, you'll get less power. Also the solar conversion depends on what time of day it is. So at noon, you can get a lot of solar energy, but obviously you won't get anything at night when the sun is set. This is an interesting problem and goes into the design of these solar power plants. And it's really a big geometry problem, because what you want to do is have direct sunlight if you can, and you want to have strong sun, and obviously the seasons matter. So think about where you live. How could you maximize the amount of sun that you can capture where you live? If you came up with the idea that you want to put your solar panel and make it movable, that is a great answer. Because what you want to do is have the solar panel facing the sun as the sun goes across the sky every day. So that's why a lot of solar plants are actually on what are called trackers, where they'll actually point to the horizon at sunrise, and then they'll follow the sun throughout the day to get the very most amount of energy. So that would be a way to maximize the energy for getting it, because not everybody lives near the equator or lives where there's a lot of sun. But it doesn't mean you can't still take advantage of solar energy. So let's get to what you're going to do. So you're going to be designing and building a hybrid wind and solar plant. So let's start with what you should hopefully have. For the solar plant, it's very simple. You're going to have two things. One of them is almost already assembled for you. It's the solar cell. This is a 5 volt, 100 milliamp solar cell. And if you point this at the sun, you'll be able to, this will act a little bit like a battery. And you have two leads, a red and a black lead. The red is the positive side. The black is the negative side. And what you're going to do is very simply, you're going to basically light up an LED. And what I recommend is that you use the white LED. I think you should have gotten a white LED for this, because this 5 volts is plenty of power in order to actually light this LED. And the way you'll hook it up is shown here. Now, LEDs, you may notice, have 2 legs, and one of the legs is a little bit longer than the other one. And it's really important that you hook this up in the right direction, because the longer leg has to have the positive contact. So you have to have the red going to that long leg. And then when it's in the sun, you should see this LED light up. Now, let's talk about your wind turbine. So this is a little bit more complicated. You're going to need a few more pieces of equipment here. What we've given you is a generator, which looks like this. It's essentially a motor. If you've done our electric vehicles lab, you may have seen that you've got a motor in that one, but this is a bit different. This is also a motor, but a motor running backwards is basically a generator. So this is the generator, and you're going to have, we've given you some blades, which are on the right side of the slide. And those are going to be your turbine blades, and you can put those on the generator. You're going to need some jumper wires, and then I recommend that you use the red LED for the wind turbine, because it takes less voltage in order for it to light. And you're not going to get as much voltage out of this generator as you will out of your solar cell. So the way this one works is, because we're running this backwards, this motor backwards, it's a little bit backwards. In this case, the black wire is going to be your positive, and the red wire is going to be your negative. So again, make sure that when you hook up your LED, that the long leg of the LED is hooked to the black wire, and the short leg is to the red wire. Okay, so those are the 2 circuits that you're going to use. Now, what we want you to do is build a little house. Now, on the left here, I built kind of an ugly little shed, I guess you could say, but that's what my wind and solar assembly looked like. And you can see I've got the LEDs pointing down, so I can see them light up even in the sun, or at least they'll be a little bit shaded. Anna and Jackie were much better designers, and you can see some of the examples that they made of basically creating a hybrid wind and solar piece of equipment that can light up a house. And then we want you to test your design. So here's a video that shows what it looks like when you put your unit out in the sun, and then you can use a hairdryer or a hair blower to try to spin your turbine so that it can light up the LED. Just be careful. Make sure that you don't have it on a high temperature, because you don't want to melt your blades. If you don't have a hairdryer, you can just blow on it with your breath and get it spinning, and you should be able to see the LED light up. So, a couple of things to think about in your breakout. Well, first of all, did you get your wind design to work? Were you able to spin the turbine fast enough so that the LED lit up? And again, as I mentioned, if you're using a hairdryer or a fan, make sure it's on a low temperature. But if you move it closer to your wind turbine and further away, do you see a difference in how much the LED lights up? How far away does it go? Do you have to go for the LED to stop lighting? Do you get the solar cell to light up when it's facing the sun? If you cover it with a piece of paper, with your hand, does the light go off, or just does it dim? If you take and face it away from the sun, what happens to the LED? Does the LED light if it's cloudy? Does the LED light if you're looking through a window at the sun? These are all things to kind of experiment with. And we'd like to see what your house looks like, and see what your design looks like. So if you like this, you might want to do some more research in terms of how these industries work. There's also what's related to the whole industry is the storage of energy, so the battery energy. And there are other types of renewable energy like hydroelectric and geothermal. There's tidal energy, where they're taking advantage of the movement of the tides coming in and out of different geographies. And as I said from the start, there's all kinds of different engineering areas that are involved in renewable energy. If you're interested in any of these various types of engineering, but you still want to work in renewables, I'm sure that there are ways that you can make that happen. If you enjoyed this lab, there are actually a lot of different things you can do to extend the lab. For example, can you make blades and attach them to your existing blades so that you can capture more wind? Or could you integrate gears into your design and make your own gearbox so that you can get the generator to spin faster? And then another thing that you can do is if you can get a multimeter where you measure the voltage of your output. That's more accurate than just looking at the brightness of an LED. But then you can put some real quantitative measures to that. Now, on the solar side, if you have multiple solar cells, if you have many groups or many students that are working together in a larger group, you can combine them in a series or in parallel circuits and see how much voltage can you get out of it. This solar cell was a 5-volt solar cell. If you put 3 together, you get 15 volts. And there's a lot of experiments you can do in terms of combining them. And again, I would recommend as an extension to get the use of a multimeter to actually measure your voltage and your current. And then finally, the renewable energy is not just all about making the power. There's also challenges and applications in the rest of the power grid that has to be solved. Problems that have to be solved. Partly because electrical energy is not readily storable. So we have a separate lab called the Power Grid Lab that helps you understand how the power grid works and also helps you understand what the challenges are and how you can control the power grid. As you know, when the sun goes down, there's no more solar energy available, but there could be wind. You can't control the wind and the sun. So how do you manage that in the power grid? So I hope you get a chance to do some extensions of your labs. Now, one other extension that I didn't actually have on the page here that I think is really cool. If you have a class where you've made a bunch of different wind turbines, try to make a wind farm. Can you hook them together in a big circuit and maybe get a box fan and see if you can get a wind farm where you have multiple turbines running all at the same time? That's another great lesson and example of how would you design that wind farm? Where would you place the turbines? It's a very practical problem that's being thought about all the time as wind farms are designed. So I hope you've enjoyed the Renewables Lab and have a better feel for how wind and solar power works. I hope you have some fun doing it. So thanks for watching. Well, hi, everybody, and welcome back to Engineering Tomorrow Labs. What we've got here is an extension lab for the Renewables Lab, which you should have done. And this is about the power grid. And what we're going to do in this lab is explain how the power grid works, how it's set up in the US, but it's really similar to how power grids are set up all over the world. And then what are the things that the engineers that are running the power grid, what do they have to do? And you're going to get a chance to do some experiments, or rather be a power grid controller as we have some simulations online that you can actually run. So first of all, what is a power grid? The power grid is essentially the grid of electrical wires, transmission substations, power plants, everything else that actually is all connected and that takes power from a power producing plant. And you'll see what some of those are, but you know what they are. They're things like wind turbines, solar farms, gas plants, coal plants, nuclear plants. And it takes those and then it basically delivers that power to people who use it, which could be your house. It could be a company, a business. It could be all kinds of different things that actually use electricity. And the power grid is a very complicated thing. So what's interesting is that this delivery of electrical power, which is produced by a power plant and delivered to a user or a consumer, has to always be balanced. So the demand that businesses and factories and homes need has to always be balanced with exactly the right amount of electrical power being produced. And that's kind of how the power grid works. But obviously, like if you're in your house and you flip on a switch, you're always expecting the power to go on, the light to go on, or your music to go on. And it's really annoying if that doesn't work. So what's really critical about the power grid is to make it reliable. So I want you to think about what are some of the things that could cause the reliability of the power grid to be poor? What could cause it to fail? And as you're thinking about that, I want to show you a video because there's a great example of what happens when the power grid fails. And that is what happened in Texas in 2021, in the winter of 2021, when they had a failure of their grid. So take a look at the video and think about what you see, what you hear about what causes the grid to fail.
We had a fireplace and I burnt up all the wood we had. This is sad. This is a sad state of affairs. I wish it were better, but somebody's got to do some planning after all this is over and make sure there's an alternative source of energy.
As we continue to manage the bitter cold, the historic storm we're seeing, we are trying to get people's power back on as quickly as possible. But in order to do that, we need to be able to safely manage the balance of the supply and demand on the grid. ERCOT's fundamental job is to maintain that supply and demand so we don't have catastrophic collapses of the system and blackouts. We asked the local utilities to reduce the amount of power they use in order to keep the overall system in Texas operating safely. We need to keep power flowing safely and effectively. And when we saw, particularly Sunday night as the storm blew in, the operators at ERCOT are thinking about that safety and that margin for safety all the time. We would not have asked for any customer to have to be without power, particularly in this terrible cold situation, unless we needed to manage the overall security of the electric grid. So when we first asked for those outages to happen, that was paramount, and remains so.
So from that video, that's just one example of an incident that occurred when a power grid failed. And probably you noticed that one of the major drivers of that was essentially unexpected weather. The weather got a lot colder in Texas that winter, that February, and the cold lasted a lot longer. That's not the only place that we've had problems with the power grid. I live up in the northeast of the U.S. in Pennsylvania. And several years ago, we had Superstorm Sandy that came in and knocked out a lot of the power grid around here. We were without power. Hopefully you can see how important this is, because not only do you lose power, so you can't turn your lights on in this dark, but you can lose your heat. Because quite often your heating system is reliant on some bit of electrical power. And you saw on the video in Texas, if there's no heat, your water pipes can freeze and burst, and that causes more and more problems. So it's kind of a cascading problem. That's why it's so important that the power grid is reliable and works for everybody. So what we're going to do in this lab, you're going to learn more about how power generation works, power consumption, a little bit about what alternating current is. And at the end, you're going to be managing two power grids to keep the lights on. First of all, to keep the lights on, to make sure that the balance of supply and demand is balanced. And then on the second exercise, you're going to get a chance to turn on and off different types of generating stations or generating sources, and try to make the overall grid more carbon friendly. So let's get started. So on the conceptual basics, I mentioned a few times here, supply and demand. So first of all, let's talk about what is demand. So demand are the things that you use electricity for. So you can see from the little house here, you've got lights, you've got refrigerator, you've got a hot water heater, clothes dryers, heater for your house, microwave. These are all demands of electricity in your home. Obviously, factories and stuff are going to have even bigger demands because they're using electricity for a lot of different reasons. Now, on the right side of the page here, you'll just see a comparison of what most residential houses use and what's the ratio of their usage of power in the US versus in the UK. So it's a bit different. In the UK, they have some different uses that are used more for their for electricity. For example, their heating, more heating is done with electricity there than in the US, which may use more natural gas and things. And in the US, actually, in the summer, we have a lot more cooling needs because of the heat, and it's hotter in many parts of the US. So that just gives you a feel. That gives you a feel for kind of how electricity and power is used around the house. So a couple of things to think about. What can cause an increase in demand throughout the year, and how can you help reduce demand? So put a few thoughts into that. All right, that's all about demand and supply, or at least demand, as far as the electrical grid is concerned. Now let's talk about supply. So electrical supply is something that you've already looked at in the renewables lab, where you had solar and wind supply. Here's a series of different types of electrical generating sources. So you'll notice at the bottom you've got your solar and wind power. A couple of the other ones you may or may not recognize. In the upper left-hand corner, looks like a futuristic factory, but that's actually a gas power plant. In fact, it's a combined cycle gas power plant where they use natural gas to heat up, to basically turn a turbine, basically the burning of natural gas to turn a turbine that creates electricity. And then what they do is they take the heat from that combustion process and they use that to make steam. And then they can use that steam at the same time to turn a turbine in a steam turbine, basically a steam turbine generator. So you have that's why it's called a combined cycle, because it's not only the turbines are turning. Some turbines are turning with gas combustion, and other turbines are turning with steam. In the upper middle picture, you have what's actually a nuclear power plant. Now, a lot of people think those two towers are the nuclear plants, but those are actually cooling towers. The nuclear core is in that domed building right in the middle there. And in a nuclear plant, the radioactive material, which is constantly heating through nuclear reactions, is being used to heat water, to make steam, and again to turn a turbine. So that is a different type of energy source to make power. In the upper right-hand picture, you'll see a hydroelectric plant where you essentially have a reservoir at a high elevation, and you're relying on taking the change in energy of the water as it falls from a high elevation to a low elevation to turn a turbine. And that then can generate electricity. And then finally, in the bottom right-hand side is a classic old coal plant. You can see the coal pile there. A lot of the coal plants rely on these conveyors that are moving the fuel, the coal, up into the boiler system, which again is burning the coal, making steam, and again turning a turbine. So these are all the various types of classic power generating units, and each of them has a pro and a con. So can you think about what are some of the pros and cons of each one? By the way, each one will have pros and cons. We talked about a little bit about the different types of generating plants and some of the pros and cons. Just hopefully you had a little discussion about it or a thought about it. Just a few tips. Obviously, with coal plants and with natural gas plants, they produce carbon. So there's a carbon footprint, much less for natural gas than for coal. The pros and the cons. The cons for solar and wind is that they're not always available. Obviously, solar doesn't run in the nighttime, and wind doesn't generate if there's no wind. So all of these have pros and cons. But the bottom line is that the most robust grid and the most robust and reliable grid is going to have a mixture of these types of sources of power. And what you can see on the left-hand side is some old data, but it shows in the world electricity production the ratio of generation by some of these various means. And you can see, at least back in 2016, coal was the major supplier or major fuel being used to produce electricity. And renewables was less than a quarter of the world's generation. And then the renewables was broken out by the hydroelectric, which you saw a picture of, and biofuels. And then you can see how small solar and wind was at the time. On the right-hand side is a graph that shows kind of a change in over time, over a 3-year period of the growth or the reduction in the use of various sources. So this again is a bit old data, but if you look at the coal bars there, you can see that over that period of time from 2018 to 2020, the fraction of U.S. generation from coal was reducing quite dramatically. And then if you go to the other side of the graph where the wind data is, you can see that it is increasing, but it is still still pretty small. But since then, things have continued to progress. Coal has continued to reduce as a share. Wind and solar has continued to increase as a share. And you'll see that natural gas is actually a very, very important and a large part of the electricity grid generation. And it's a relatively low carbon. It's not zero carbon, but it's better than coal from a carbon footprint point of view. And it also has a lot of other advantages, like being easy and quick to turn on and to turn off. And basically, these are just some of the advantages for it. So again, a mix of supply sources is quite important for the grid. So the grid is, as I had mentioned right from the start, really just a lot of wires connecting power producers to power consumers. And this picture is an example of, or a demonstration or a representation of the various power grids that we have in the U.S. It is not one solid grid at this point, but they are connected. But they do tend to be divided into various regions. And you can see on the right-hand side some of the names of these various electrical regions. You can see the ERCOT down in Texas. In the Northeast, New York State has its own. And also where I live in the Mid-Atlantic there, you can see one of the grids called PJM. And basically these are connected in general. ERCOT is less connected to the others, but essentially these are all kind of small grids that are all connected together. In order to stabilize the grid and make sure that you've got the ability to make up problems if something goes wrong, if the wind suddenly shifts, or if you have a outage because of severe weather, the best thing you can do is to have energy storage. But energy storage, or at least storage of electrical energy on a large scale, is very difficult. And there's a lot of work going on to try to improve that, obviously battery storage. But let's take a look at this video. It'll give you a feel for for some of the challenges and some of the various means of energy storage.
Electricity storage. Electricity storage systems are the set of methods and technologies used to store electricity. The need for electricity storage is due to an imbalance in supply and demand on the electrical grid due primarily to an increase in renewable energy generation. These supply and demand discrepancies occur because renewables are intermittent, meaning electricity isn't produced when the sun isn't shining or the wind isn't blowing, even though consumers still require electricity in these renewable downtimes. Currently, grids distribute electricity in real time, meaning electricity is being consistently produced to meet consumer demand. Electricity storage gives grid operators the flexibility to use electricity that otherwise would be wasted. This grid flexibility is highly sought after and has the potential to transform how we produce and consume electricity, and is therefore being widely researched and tested. There are many different forms of electricity storage, the most common being battery, pumped hydro, compressed air, and flywheel. Currently, the largest challenges in implementing electricity storage at the grid scale are the cost and the infancy of the technology. That's electricity storage.
Okay, so let's talk a little bit more about energy storage. You heard a little bit about it in that video. Batteries, obviously, is one source of energy storage. So it's one that you'll know very well. You'll recognize a classic AA battery. So that's obviously good for small electrical needs. And essentially, these are electrochemical cells. Most of these batteries are essentially real chemical processes that charge and discharge. Well, they don't all charge. For example, these alkaline batteries can't be charged, but there are other types of batteries that can. You may have heard more about this in our electric vehicle lab if you're interested in battery technology. Another way of storing energy is through compressed air. So the concept here is that when you have extra power, extra energy from a power plant, what you can do is run a motor and compress air kind of as a stored an energy source. So what they could do is they can store this compressed air underground in salt caverns and other places. So then you basically are using extra energy or extra power when it's not needed by the consumer or the factory. You're compressing the air. And then when you need power, when there's not so much power available on the grid, you can decompress the air, bring it out, and turn a generator with it, and you've got essentially a battery. So that's one option for energy storage. Another option is kind of creating I'm not going to call it artificial, but essentially a hydroelectric plant, a hydro plant on demand, kind of like for hydro energy. But what you can do is do pumped hydro. By the way, this is not hydrogen. This is water, hydro as in water. And what you do, again, when you have extra generating capacity, you turn on your pumps and you pump water up to a high reservoir at a higher elevation, and it has more potential energy. And then when you need that power back, when there's less power being generated on the grid, you can then release that reservoir and then turn your turbine and turn it back into electrical energy. So that's pumped storage or pumped hydro. In transportation, there's actually another type of way, another way of storing energy, and that's the flywheel. So essentially, if you have a flywheel, which is a mechanical device that's heavy, if you get it spinning, for example, when you have extra power, there's energy in that spinning flywheel. And then when you need extra energy, you can extract that energy by slowing that wheel down, turning a turbine with it. And it's a way of efficiently storing rotational energy. This is much more used in, say, automotive and as I said, transportation applications. And then there's all kinds of new ideas that people are coming up with. This one's called the energy vault. If you look at the video there on the right-hand side, what they have are just a bunch of huge concrete blocks. And instead of, this is kind of like a little bit like that pumped hydro where they pump the water up and then when they need it, they let the water go down again. In this case, you're actually using extra energy to lift these heavy blocks up to a high elevation. And then when you need to recover the potential energy that you've created, what you do is you release the blocks and then that can be converted into electrical energy. It's a bit futuristic, but I know that there's work going on in this and other types of energy vaults for storing electrical energy. Well, let's get to some of the stuff that you're going to do now. The first concept that you need to understand is a little bit about AC, or alternating current frequency. As I mentioned, you're going to be doing two exercises. One is to keep the supply and demand balanced. And in order to do that, or if it's not balanced, if the supply and demand on the grid is not balanced, what happens is that impacts the frequency of your power. So first of all, what is AC? What is AC power? So electrical power, it can be, or a circuit can be an alternating circuit or a direct current circuit. A direct current circuit is one that's probably you've seen in some of our other labs, where you basically have current running in a circuit, in a circle, and essentially it goes from a source like a battery, it goes through a load, and then it comes back. So that's the flow of current and the flow of electrons. Now, the power grid runs a bit differently. It runs in alternating current. So what you have is your electrical electrons are oscillating back and forth. And current is basically just the movement of electrons. It doesn't mean that it has to all go in one direction. The movement of electrons can be back and forth, and that'll be just as good for powering things. And the power in your wall, in your house, is alternating current. So whenever you have something that's alternating, you also have extra parameters that describe it. And one of the parameters is the frequency at which it alternates. So in this country, alternating current is usually, is always alternating at 60 hertz, which is essentially cycles per second. So it goes back and forth 60 times every second. That's the frequency of power. Now, if there's not a match between supply and demand, that will change that frequency ever so slightly. But there's a limit, there's a bound with which that has to be maintained. And what you're going to do is you're going to balance supply and demand, like a grid operator, to make sure it stays within that limit. Now, in Europe, the actual alternating current frequency is 50 hertz. And what you're going to do is you're going to be doing a simulation here that is actually a European simulation. So your target is to try to keep the frequency of the alternating current at 50 hertz. And the way you'll do that is, you can see the graphic here. You're going to have the ability to change the supply and demand, change the supply of some of the various sources of power. And then there's also one option to change the demand. So you can turn up and turn down the factory there and how much electricity it gets. Now, one of the things you can't control is how much wind power and solar power you have. So that's going to be varying on its own. And you're going to be then accounting for that by changing the other things, by changing these sliders. So hopefully you'll get a feel for what happens if you get too far out of bounds. You'll have a blackout. So you'll get a chance to get a feel for what a grid operator does by playing this game and keeping supply and demand balanced. The last exercise here is a part of this extension is to understand another thing that you really want to do, which is to try to reduce the environmental impact of the power grid. Or rather of the power system. And in this case, you're going to have what looks like a much more complicated grid. You're going to have places where there's demand. So you'll see a place called Industryville near the bottom. Up near the upper right, there's a Residenceburg and a commerce town. And they're all using power. then you have the ability to change where you're going to get your power from. So in the middle, you'll see there's a supply. There's a natural gas plant, a hydroelectric plant. Those are plants you have control over. Down in the bottom left, there's a coal plant. Kind of down in the middle, there's a nuclear plant. There's also wind power, and that's something that you don't have control over. So there's going to be some natural variation in how much wind power you get, and you're going to balance that with your other sources. Two other things as a part of this little grid, there is two external systems that you're connected to. In the upper left, you can see the external system 1. So that could be exporting power to another mini grid. And then on the right hand side, there's external system 2, where you can export power to or input power from another grid. So the goal here is to get a feel for how do you reduce your carbon footprint. So you might want to back off on your coal plant. You might want to turn on your nuclear plant. But all along, you have to make sure that you're maintaining safe usage of the grid, basically the wires between all these substations and all these sources and sinks, and also minimize the carbon footprint and keep it running so you don't have a blackout. And as a part of that, it looks pretty complicated, but here are a bunch of challenges that you can run to see if you can actually achieve. And we do have a student workbook for this extension lab. So you'll be able to walk through that student workbook, and these challenges are explicitly shown in there. And also the explanation and some advice for the first challenge is also in the student workbook. So if you are interested in this, or if you enjoyed this, or if you're interested in renewable energy and kind of how the grid works, there's more that you can learn, a lot of applications you can get to. You'll see the type of engineers that are working in this industry. All different types of engineering is needed. But one last thing I want to point out is you see that there's a TED Ed talk that's actually really cool. And it's entitled, "What Does the World's Largest Machine Do?" And if you just Google that, you'll find, I think it's about a 4-minute TED talk that explains the world's largest machine, which basically is the U.S. electrical grid. So it's quite a good explanation of a lot of the stuff we just did, or we just talked about. So hopefully you'll enjoy this extension to the lab, and you'll be experts at how the power grid works. So good luck.